Thank you very much. Welcome everybody to the last of the 12 webinars of the Festival of Mathematics this week. We have today a session on teaching mechanics. I'm Will Hornby. I'm subject advisor in mathematics at OCR and also the subject development lead for A-level maths and further mathematics. So. Without further ado, let's have a look at what we're going to have a talk about today. So this is an overview of the session. We'll have a quick look at the new content for mechanics. I'm sure most of you have got your heads around this already, but I just want to pick out some bits and pieces, have a think about what content's gone and what sort of looks the same but actually is slightly different. We'll look at some of the key concepts in the mechanics content, and some of the misconceptions and ideas that are worth thinking about in teaching. So run through some of those, and as we do that, we'll take a look at some of the questions in the sample assessment material and how they reflect the new overarching themes in particular as applied to mechanics. We'll then have a quick look at the end at some ideas for using technology and some practical work ideas as well. So do feel free, please, to ask questions as we go along in the chat box, and I'll either pause and go through a few at a sensible moment, or leave some to the end as is appropriate. So do please throw them in, and I'll try to leave a good 10 minutes at the end for further Q&A to cover anything in the presentation or outside. The last thing I should just say is that the intention here is to talk about teaching mechanics for A-level maths. There's no specific content today about further mathematics, the mechanics of further maths. So the new content. This is what the new content looks like. There are 4 sections, quantities and units in mechanics, which, to be honest, you can pretty much ignore. There's just 2 little statements in there, one about units and one about compound units. So if you're teaching mechanics, you're going to end up teaching these. The last one, statics, 3.04, is moments, study of things that aren't moving in terms of statics. There's a tiny little bit of statics, which has been put into the A-level maths content only. It's not in AS. And to be honest, this is basically an application of proportionality. You could teach it to year 7. It's there for completeness, because it feels a bit strange that somebody might have done mechanics as part of A-level maths and not thought at all about moments. So that's why that's in there. And then we have kinematics and dynamics, which form the main chunk of things. So kinematics is a study of motion without thinking about forces involved, and dynamics, study of motion by thinking about the forces involved. So generally speaking, various problems fall into one or other of the camps, but a lot of the time we mix the 2 together. So we might start knowing some stuff about how an object is moving and use that to work out what forces must be acting on that object, or vice versa. So sometimes we think about the areas on their own, sometimes combining together. And it's often the combinations that within assessment certainly form longer, more problem-solving questions in which students find harder to make that connection between the 2. So what's changed from where we currently are? So here are some broad strokes about what's changed. Certainly the vectors. Currently, component form of vectors is specifically mentioned as not required in Mechanics 1. I mean OCR, of course, Mechanics 1. And vectors are used throughout the course, but they're played down quite a lot. So now they take centre stage, in particular A-level, and even more so in A-level further maths. So there's not necessarily very much in the AS, but once they're really confident with vectors, A-level maths takes things on into 2 dimensions, including bits of vector calculus and so on, which is worth pointing out. So the other thing to say about vectors, the other main change, is that in AS mathematics, the vectors are always given collinear or perpendicular, so parallel or perpendicular, or in 2D component form. So the whole idea of resolving a force into components is left until A-level maths. I think, a slightly controversial choice of content by ALCAB, the A-Level Content Advisory Board, but it is there, it is what it is, and I think many people will simply teach resolving forces as they go through. But that being said, we'll see later on in some AS sample assessment material the sort of way that we'll present problems involving forces at AS. No linear momentum, so there is currently linear momentum on M1. That's now gone into further mathematics. The linear qualification. Now, whilst a lot of the content looks familiar, the current M1 course, of course, has as its assumed content Core 1 and Core 2. So it's worth remembering that this M1, and it's an AS unit. It's worth remembering that this mechanics content, while it looks very familiar, has its assumed knowledge Core 1 to Core 4 and is assessed in the A-level exam at A-level level of demand. So you might find yourself looking at the sample assessment material and thinking, oh, that's a bit nasty. That's something that's a bit harder than we currently asked on M1. Well, that's how things ought to be, because overall, over the pure, the mechanics, and the statistics in the three A-level exams, that has to be that full range of the same demand as at the moment. And rather than keep the mechanics all at AS level of demand, we need to spread the demand up from E grade at AS right the way through to the A star at A level. The last thing on the list there is calculators. The main change in calculators, of course, is to do with statistics, but it has a backwash effect here into mechanics. So the criteria requirement that students have calculators that can access the binomial and normal probabilities means that the students have something, for example, like the scientific calculators, the Texas 30X Pro and the Casio 991EX Class Whiz. Those are sort of scientifics that do those. They're also able to do a variety of things such as solve quadratic equations and sets of simultaneous equations and so on. Find the gradient point of the line and definite integrals. And so these sorts of things in the OCR specifications, in both OCR A and the OCR B MEI, we have the rule that students can use their calculators for any functions that the calculator can perform. So we do expect a little bit of offloading of calculation onto their calculators. We'll come back later on with some examples, but one of the great things here is that particularly in mechanics, so many marks in current mechanics exams are really being given for pure mathematics skills. And within the new world, we're testing those skills within the pure math sections. And so it's quite nice to be able to give only one or a couple of marks for solving some simultaneous equations, or a single mark for solving a quadratic, and also not having to worry when setting questions up that the quadratics or the simultaneous equations come out with nice coefficients all the time. So we get much less synthetic questions going on. So again, if you're looking at sample assessment material and you think that's a nasty quadratic for them to have to solve halfway through this question, remember that we're expecting them to offload onto the calculator during the exam. You'll be wondering, of course, what happens if we want them to solve things. We have a detailed reasoning statement, which pretty much never appears in the mechanics and stats. It appears in one place in the further mechanics, where we want them to produce that full analytic solution that doesn't rely on calculator functions. So calculators worth picking out there as a change, even though it's not strictly content. So where has all the content gone from current M1? The current M1 is the lighter grey at the top, and current M2 in the dark grey. So the new content is a mix of the current M1 and M2. Linear momentum has gone off to AS further mechanics, of course. And if you're thinking, well, that probably makes this mechanics a bit bigger, we do need to remember that in the new GCSE, students will have done some of the kinematics before, so they'll have thought about a gradient of a graph as being rate of change, the area under a graph, and so on. And they will have met at least the SUBAT, the kinematics equations. And it will depend, of course, on your students, and if you're teaching GCSE, on your students and the level that they're working at. But some will have seen some sort of derivations and ideas behind those SUBAT equations as well. So there's that to be said there. Okay, So the OCR specification, this is what it looks like. This is stage 1 and the stage 2 in the A-level spec. Stage 1 refers to the first 2 terms of a 5-term A-level. And the reason we've done that is that matches up to the AS. It's not really sensible to talk about year 1 because year 1 suggests the whole of year 12. And in fact, the AS is only 40%. So AS content really should be thinking about covering in the first 2 terms, even if you're not taking AS. You don't have to cover exactly the stage 1, but it's there as a suggested sensible progression. And then the assumption is that you'll spiral back around that stage 1 content as you go through stage 2. So as you're teaching terms 3, 4, 5, you take opportunities to come back to that stage 1 content, to reinforce it, to draw in perhaps some bits of the pure course that you're teaching that you've now taught, and to sort of up the level of demand. You certainly can't teach all of this stage 1 content to your year 12s at, as it were, a 2 level of demand. You'll notice that there looks like an awful lot of content in the OCR specification. That's because we tried to be helpful here. This page, for example, in the DFE criteria, simply says understand and be able to use Newton's second law for motion in a straight line and so on, and then to be able to extend the use of Newton's second law to situations where forces need to be resolved in part 2. So what we're adding in here is exemplification, and in part wanting to make clear in this section how this resolving forces things work, also looking at notation, making it clear what notation is expected and that the students should have seen, and also in the EGs building in some of the contextual sort of things that pop up in mechanics. We have this situation where 40% of the current OCR centres don't teach mechanics to A-level maths students. Many of them will teach it to their further mathematicians, of course, but there's going to be a lot of people teaching mechanics for the first time come September. So these standard mechanics tropes like passengers riding in lifts holding parcels and cranes lifting weights and so on won't be familiar to those teachers. So we tried to include some of those standard mechanics context within the content. So key concepts. These are 3 things that I'd like to talk about, and briefly, but with a view really to the teaching and learning aspects of these, using sample assessment materials just as example sorts of tasks. So modelling assumptions, equations of motion, and Newton's laws. So the modelling assumptions. One of the changes, big changes in the new specification is these overarching themes which have to be applied across the content. And overarching theme 3 is about modelling, and there's an assumption there that we do a bit more than simply using standard models, that we spend time thinking about setting models up and about interpreting the outcomes of models, both in terms of what does this number mean when I put it back in context, but also given this output, does this mean it's a good model or a bad model, doing some actual evaluation of the models. And of course, built into all of that is modelling assumptions. So in mechanics, we have to make a lot of modelling assumptions all the time. In reality, objects are subject to a huge number of very complex forces. And in A-level mathematics, we have to abstract a long way down because the techniques that they have are relatively simple. And they may seem extreme sometimes, but of course they do provide pretty good predictions a lot of the time. Now, the trick is knowing not only what modelling assumptions are being made in the standard context, but also understanding what effects these modelling assumptions might have on the outcomes of your modelling process. So, for example, when you're throwing a ball, we're making an assumption, making the assumption that the ball is a particle, gravity is constant, there's no air resistance, all these sorts of things. And in each of these cases, you can have a think about what not only do we want to in the classroom talk about what the assumptions are, but also what would happen if that was not the case. So if we throw a ball when we're up on the top of Mount Everest, what difference will it make? Thinner air, less air resistance won't make much difference. Gravity, well, yes, it's a bit smaller, but not very much, and so on and so forth. So trying to build in the whole of the modelling cycle as we're going along. So we have also here smooth rough contact. We use the Coulomb model of friction in A-level maths as always, and in reality, that's a terrible model. And most of us, when teaching, simply get on with teaching it. And this is how friction works without thinking about it very much. In reality, dynamic and having a difference between dynamic and static friction, i.e. the friction between surfaces that are stationary or in relative motion, there's usually a great difference between those. And if you imagine yourself pushing a block along a rough table, to use nice abstract terms, as you push into the block and it's not moving because the friction is holding it in place, as you push hard enough for the friction to break, you get a sudden jerk forward because, of course, the static friction is much higher than the dynamic friction. So you get this sudden release of friction. In the Coulomb model that we use for A-level maths, the standard model, you simply get a linear increase of friction until the moment at which it breaks, at which point the friction opposing the motion is exactly the same as it was at that moment when the friction broke. So we don't get the jerk forward, and in fact, the behaviour that we get out of the mechanics model is not what students would expect from reality. Smooth pulleys. What's smooth about a pulley? Of course, if the contact is between the rope and the pulley is smooth, then it doesn't do anything. It's the same as a smooth peg. So when we're talking about a smooth pulley, we're talking about that it's free to rotate around its axis without losing energy. So just worth refreshing your mind about what these modelling assumptions are, and also, as I say, having a think about what differences it might make. So here is how the overarching themes and assessment objectives match up. I want to just draw on this because it's the overarching themes really that you ought to be thinking about in terms of teaching and learning. So the overarching themes come with the content from the A-Level Content Advisory Board and from the Department of Education. This is the criteria about what goes on in the classroom. The assessment objectives are from Ofqual, from the regulator, and the point of the assessment objectives is really to make sure that the different awarding organisations treat all of the overarching themes and do so in a similar way with similar interpretations, and do so to similar proportions within the assessment, so that there's no sort of major difference in the way that the approach works. So the assessment objectives really those are tools for the regulator to make sure that the awarding organisations are assessing it correctly. The overarching themes are really the tool, and the mathematical modelling overarching theme does talk about the complete modelling cycle. There are aspects in there which are very difficult to assess in a sensible or valid fashion, and certainly within the assessment it's almost impossible to assess the whole of a modelling cycle, because if you allow students to set up a model within assessment, the work that they then do following that will depend on how they set it up in the first place. So you instantly get situations where their solutions aren't comparable. And in a similar way, you can give them a model, get them to evaluate what's going on with the model, suggest some changes you might make to the model, all a very good thing, but you can't really go back round the loop and start and say, okay, if we've done that, what difference does it make? Because then the work that they do will depend on the sorts of changes that they make. And those are very important experiences in the classroom. We abstract so much in mechanics in order to pare down to the techniques that are available to the A-level student. I think it's a really valuable experience to students to say, well, if we do put in air resistance, how might we do that? And if we say it's proportional to velocity, well, very quickly I find myself in a situation where I can't solve the equations anymore. So I think it's worth seeing, worth passing on into higher education students who are aware of the simplicity of the models that they're using, and how things might be improved or made more complex. So this is what Assessment Objective 3 says. Because we're going to look at some assessment items, these are the three strands. So we have this translating situations and context into mathematical models, so setting models up. And that does include setting up standard models, so extracting from context a force and acceleration, a mass, setting up a sort of F equals ma type thing. Using mathematical models is the main chunk of it, which is using given or set up models. And then 3.5 is really the difference in the new specification. 3.5 is about evaluating the outcomes of modeling in context, recognizing the limitations of models, and, where appropriate, explaining how to refine them. So this is the key difference to think about in terms of teaching, in terms of exam preparation, in terms of the backwash from the assessment. into the classroom is this aspect of evaluating the outcome. So here's an example. This is a question on projectiles from the OCR sample assessment material. It's a fairly standard, though perhaps tricky. It is question 12, of course, so it's right at the back end of the paper, but a tricky sort of A-level standard projectiles question. And you can see here the basic format that we're intending to use for modelling questions. We want to set up in the STEM what the real world situation is, and then talk about modelling assumptions that we need to. So we start with the real life context, translate into the model, and then we do the work in the model. And it makes it clearer for students, once they get onto the interpretation stage, where it is that they're sort of interpreting back. What's the original context that they're supposed to be working in? Whereas if you mix into that STEM all this stuff about initial velocity being u and the angle of projection and it being a particle, tends to blur the lines between those two things. So this is the standard sort of setup, and the first few parts are about finding this value of u to make the ball land on top of the hoop, and so on and so forth. Now let's just have a think about this model. In many ways, this is of course a terrible model. If you imagine what would actually happen if you were out throwing a netball at a hoop, what happens to this ball? This ball is a particle, of course, rather than a sphere, and it's at rest for a while, and then suddenly, sort of magically, it zooms off at this u meters per second at exactly 40 degrees, instantaneously accelerating to whatever that u is. It then produces this beautiful parabola, and of course no real life object outside of a vacuum will produce a beautiful parabola, and it lands right on top of the pole that the netball hoop is on. So there are all sorts of things that we can think about here that are relatively simple for students to think about, which don't make a lot of sense in terms of a direct model and of how things differ in the real world to the model. So this is then the penultimate part of the question: how appropriate is this model for predicting the path of the ball? And you'll see here this is assessment objective 3.5, so thinking about the back end of the modelling cycle and various straightforward things. And you'll see in the mark scheme this EG. Where there's an EG or a few EGs there, those are simply possible examples of things that students might say. As we do at the moment, and standardization meeting after the assessment, the markers who've browsed a large number of scripts before going in will arm themselves with lists of possible solutions to this sort of question, and they'll come up with, here is a list of acceptable for the mark, here's a list of not acceptable for the mark, and some sort of rationale behind it. So this is sort of work that goes on behind the scenes in the marking. And so you can be confident we're not trying to get exactly these words, they're simply examples of the sorts of sensible things that students might say. And the last part of the question about improvements. So this is 2.5c, how could we improve the model? So here, yes, of course, we could change the ball into a sphere so that the air resistance comes in. We could change the angle to a variable, so we could allow for either error in throwing it precisely, or simply that she might want to change the angle at which she's throwing it. And the key thing for me with this model, you could improve it enormously by turning the hoop into a line of points, so that we have a range of values in which the ball could fall for it to count as a goal. So various things to think about there in the modelling assumptions. So equations of motion. Let's have a think about equations of motion. This is the second key concept here. So equation of a motion is a function of an object's acceleration, velocity, position, and time. Generally speaking, in AS and A-level mathematics, it's either the acceleration in terms of time, the velocity in terms of time, or the position in terms of time. We don't tend to mix up acceleration, velocity, and position. So they're functions for those things in terms of time. And they could be scalar or vector equations. So these vector equations, which any of you who are certainly who are current MEI centres will be familiar with operating with these sorts of things. And then we use calculus to move between these forms. So, of course, velocity being the rate of change of position, acceleration being the rate of change of velocity. So we can differentiate to go one way and we integrate to go back the other way. So this is a clear example of an application of the pure content within mechanics. And in those terms, this is a really nice topic if you're thinking about mixing up the teaching of the applied and pure maths. This is a very easy topic in which to do it. As you're teaching calculus, you can simply drip feed in a bit of kinematics, talking about equations of motion as you're going through the calculus topics. And suddenly your students will find themselves having done a whole load of kinematics which they didn't realize they'd done. There's no need, of course, to do that mixing. There's nothing wrong with continuing with a sort of two-teacher, one does pure and stats, one does pure mechanics, and you keep the applied as separate topics. Nothing wrong with doing that at all. But there is the option, perhaps within the linear course, to start a bit of mixing and matching. And if you want an easy way in, equations of motion are a good way in. So when we're talking about equations of motion, we're talking really about dynamics, because we're talking about thinking about the motion of a particle and not thinking about forces involved. So here's an example from sample assessment material. This is a student attempting to model the flight of a boomerang, and now that you've got your modeling heads on from the previous section, you might be looking at this and thinking it's a pretty terrible model. It's an awful model. We don't happen to ask in this question about the modeling aspects. But we certainly could. And I think that's worth highlighting, that whilst we have this whole modelling cycle, we want them to be evaluating models, talking about assumptions. It's not happening all the time in the assessment. It happens here and there. It's a couple of marks. It's enough for it to change the tenor of the whole paper, but not certainly of every question. So here we have an equation of motion which is highlighted. This is the displacement in terms of time. It's a nice cubic equation. So briefly speaking, what's going on here? Well, we can determine what happens at t equals 6 by shoving t equals 6 into the equation, and off we go, we get the displacement. We can find the greatest displacement. Now the greatest displacement, if we think in terms of pure mathematics, this is an optimization question. What we're looking for is a maximum. So we might decide to differentiate it, ds by dt. There's 18t minus 9 over 2t squared, set it equal to 0 to find the turning point. Check that it's a maximum rather than a minimum, and we'll found the time at which there's a stationary point. We can put that back into this equation to find the displacement. In terms of mechanics, we tend to think, well, the moment of greatest displacement is the moment where the velocity is 0. It moves away from me, and at some point it will decelerate, slow down, and turn around again. So we want to find v, and of course to find v we differentiate, so we get v equals 18 so on, set it equal to 0 because it's stationary. It's a stationary point. That's a link that we often don't make with students, and so on. What we don't tend to do is check that it really is a maximum. We simply say, oh, it's 0, and we rely on the context. So there are both links to be made here between the pure mechanics and also differences, because we have the contextual information about the fact that the boomerang is going away from us and coming back. We can be pretty sure that that's going to be a maximum point. We don't need to check. Now parts 3 and 4 are interesting here, because part 3 is actually an occasion on which you could use, if you felt like it, your calculator. You've got the displacement, and your calculator will give you the gradient of the point. So you can simply ask it to find the gradient of that, even these scientific calculators, the gradient of that function at that point. So this does improve access perhaps for students who are less confident or unable to differentiate accurately. This certainly gives a nice way of being able to check your answer to make sure that what you're doing is all right. Whereas part 4, find the acceleration, well, in order to get the acceleration, we're going to need to have differentiated to get the velocity, at which point we could either, again, use that gradient at a point, if we know that acceleration is a gradient of velocity, or differentiate again. Now, the fact that you can use the calculator in part 3 is certainly no reason to. It's only 2 marks, it's very straightforward, and most competent and well-prepared students will simply be able to differentiate, shove one in and get the answer. So yes, there is an expectation that there's the use of calculator, but it's when appropriate, or when necessary, if you like, to bring in. There's no requirement to do so. So here's another example of equation of motion. I want to pick this out because this has the vector equation. So we have r equals 2t cubed I plus 5t squared minus 4tj. And simply, for those of you whose mechanics is rusty or non-existent, that dealing with both the horizontal and vertical components of the position or the velocity or the acceleration at the same time is very straightforward because they're perpendicular to each other. And there's a sort of general rule that in mechanics, perpendicular things don't interact with each other. So if you want to differentiate this, you can simply get the vector v as 6t squared I plus 10t minus 4, and simply differentiate the separate things. So that's just worth highlighting as being a non-scary thing. So the third key concept I want to pick up on is Newton's laws, and really I want to talk about Newton's third law, because this is a common area of misconception and misunderstanding. But let's just whiz through the first two for the sake of completeness. So Newton's first law tells you that particles at rest or moving with constant velocity will remain at rest or moving with constant velocity until acted upon by an external force. So much so good. If you don't do anything to an object, it keeps doing what it was doing. But there's a key thing here which is worth picking out, which is that this works backwards as well. So if an object is moving with constant velocity or is simply at rest, that tells you that there is no external resultant force acting on the object. And that's the key really to equilibrium and the equilibrium condition, which is simply that you have these zero resultant forces. And Newton's first law is important because it gives us this inertial frame in which we can operate. So you can think in sort of relativistic terms if you like, not on spec, but let's just mention it, that if you've got an acceleration going on with a particular force and you've got something else going on in a different direction and in a perpendicular direction, the reason that they don't interact is again to do with Newton's first law, because you have an inertial frame in one direction and it's all fine. So just worth throwing that in there as well. So Newton's first law, let's make sure that we think about it in both directions. Now Newton's second law is the key thing that draws together the kinematics and the dynamics and the kinematics and the dynamics. Sorry, I misspoke. So the dynamics, thinking about forces, finding resultant forces, will then lead into using Newton's second law potentially to find an expression for acceleration. Once we've got that expression for acceleration, we're in the world of kinematics, because we now have something about simply the motion of the object. So Newton's second law is the bridge between those two strands. Generally written as F equals ma, particularly because we don't think about the sort of momentum, rate of change of momentum aspect of it within A-level maths, and particularly with linear momentum having gone into further maths, it'd be quite tempting to leave that out. You'll notice that these are written as vectors. That's because we, of course, in the A-level, will be expecting to operate this in 2D in vector form as well. So here's a question. This is coming back now to the idea of what happens at AS. This is an example of forces being given in component form. Classic mechanics example of a ship being pulled by two tugboats. Not a context which most students will have come across, but in real life, but they'll certainly have come across it in every mechanics textbook. Now, in the current world, we would probably ask this sort of question, talking about the ship with two tugboats with magnitude and direction for each of the forces, which students would resolve and so on and so forth. That simply won't happen in the new world. So in the new world, this sort of context ends up with the forces being given in component form. It takes a whole step out, which in many ways is helpful, particularly for the E-grade sort of end of students, because in order to find the resultant force, they don't have to jump through the hoops of doing the trigonometry. So there are fewer opportunities for them to sort of fall over on some of the basic, as it were, pure mathematics, the geometry of it, and they can get on with applying their mechanics knowledge. So why does the ship continue to move directly east? Well, if you add together this 350i plus 400j and 250i minus 400j, you'll find that the two 400s cancel, and we simply end up with 600i. So there's only a force acting in the east direction. Note that I and j are east and north, not horizontal and vertical, and so it must simply continue to move directly east. The other reason, if you're thinking a sort of more meta way, the other reason why it must continue to move directly east is because this is an AS assessment, and therefore it can't move in any other direction if we want them to find magnitude and direction. So that's worth picking out as well. So finding the acceleration, once you've got that resultant force, this is Newton's second law, as we were saying. So we were working within the world of dynamics, thinking about the forces. Now we use F equals ma to take that resultant force to find the acceleration. And now in part 3, we're working in terms of kinematics. We can ignore the forces. Now we've done the thinking about the forces. Now we're simply working in terms of the acceleration, velocity, distance, and so on. And back into Suvat equations, because you find the acceleration is constant. So this is the transition I was talking about. Is the idea of these longer questions which draw through from forces from dynamics into kinematics or the other way, and just trying to help students to understand which bits of information within the STEM are going to apply to which part of the question. So Newton's third law. Newton's third law tells us every action has an equal and opposite reaction, and the standard context we often think about is this box on a table thing, where we have the weight W acting downwards, and we've got this reaction force acting upwards. So far, so good. And they are equal, and they are acting in opposite directions. So this is an example of every action has an equal and opposite reaction. Actually, it's not. This is not the reason that W and R are the same and acting in opposite directions has nothing to do with Newton's third law at all. It's an example of Newton's first law. So these objects are static. The box isn't moving, and so the forces of acting on the box must have a resultant of 0. And one way you can get a handle on this is to imagine, say, pushing down on the box. So if I push down on the box, on the top of the box, W is not going to increase because W is simply the weight of the box. But in order for the box not to disappear through the table, start accelerating towards the floor, the reaction force, that contact force between the box and the table, or the force, to say it better, the force on the box from the table will have to increase so as to balance it out. So as soon as we start pushing down on the top, R is going to increase, but the W will stay the same. So suddenly they're not equal and opposite. So there must be something else going on. Alternatively, you can think of pulling, lifting the box. And once we start applying that lifting force, again, the weight of the box doesn't change, but while we're still applying a force that's less than the weight of the box, R is going to start decreasing because the whole thing is in equilibrium. And at some point, when we get to the point where the upward lift is the same as the weight, we'll end up with it losing contact because R is 0, and then after that, we're lifted off and the contact's gone. So a very simple situation, but an easy misconception within it. So what is actually going on with Newton's third law? Well, Newton's third law tells us that forces come in pairs. So when we think about the weight is the force of the Earth on the box. So we mustn't forget also the force of the box on the Earth, which comes as the matched pair. Now the force of the box on the Earth is pretty tiny, doesn't really do very much to the Earth, but it is there, and that is the Newton's third law pair, is those two pairs of forces. So what is the pair that goes with the reaction force? Well, here it is acting at the same point with the same magnitude in a different direction. You can think about it in these ways. As the box attempts to accelerate into the table because of the gravity, it exerts on the table a force equal to its weight because there aren't any other forces acting on the box. Of course, if we were lifting it, it would be exerting on the table a force a bit less than its weight. And whatever that force is, the table then must react with a force on the box equal to the weight. So we have this matched pair. The box is exerting a force on the table of R, and the reaction to that is the table exerting a force of magnitude R on the box, which is that normal reaction force that's coming back. So were we in this context to start lifting the box or pushing down on the box, both of these R's would be changing. Both of these R's would be getting greater, smaller, or larger in reaction to that. Bad use of the word reaction. So when we draw this diagram, we need to be careful what we're thinking about. When we draw this diagram, we're talking about the forces on the box. And it can be quite dangerous to have a diagram with lots of different objects in, drawing lots of different forces, some of which are acting on the object in question, some are not acting on the object in question, And in fact, we have the table here, all sorts of forces acting on the table, but there aren't any of those marked in. So we want to be clear when we're doing dynamics, and certainly when we start resolving forces, that all the forces that we're talking about are acting on the object in question. And that's why we draw these three body diagrams. So this is now a diagram of the box and the forces acting on the box. The box is a particle, and we've only got that object and those forces in place. And that's one way of just helping to get over this issue. And if we think within this pair, within a free body diagram like this, that we have a Newton's third law pair, then we're wrong. We're either wrong because they're not actually a Newton's third law pair, or we're wrong because only one of them is acting on the object in question. Okay, so that's some background behind the misconception behind Newton's third law. Worth trying to draw into the teaching and learning, make sure the students really understand how that operates. Okay, so last 5–10 minutes, we're going to have a quick look at some technology, and then a talk about practicals, how we might draw some practicals into the classroom. So, calculators. So in the OCR spec B, A and spec B, I've already mentioned this. Allowable calculators can be used for any function that they can perform. So in the mechanics questions, you could be using a calculator to do, for example, any of these four things. There aren't many other things that you might want to use your calculator for, other than sort of basic arithmetic and so on. And I will just reiterate that this is about appropriate use of technology. So it's using technology when it's sensible to do so, when it's going to save you time effectively to do so. And in a lot of cases, the little bit of calculus and substitute a value isn't going to take you very long, and your well-prepared and fluent students are going to find it quicker to do that by hand. But they will find themselves doing the sort of classic resolve forces in both directions and set up, and then you suddenly find yourself with a complicated-looking simultaneous equation. They may well find themselves then wanting to save time by offloading the solution of that onto their calculator. And it's worth picking out the gradient of point and definite integral. We've mentioned the gradient of point already, but within kinematics, it's worth remembering that these calculus techniques, when they pop up within kinematics, and within a mechanics question, what we're wanting to test is, do you know that this technique is the necessary thing to think about here? And it's not about testing necessarily the pure mathematical technique of doing it. And again, this opens access into the mechanics, which is traditionally a topic that weaker students find hard because of that reliance always on the pure techniques. And this really opens up access to particularly the back end of the modeling cycle, the evaluation sort of parts. And if you can't find an answer, you can't really do the evaluation. And this opens that up to more to weaker students. This is about appropriate use of technology and about technology permeating the specification as we're required to do. So this is an example. This is the same example as before. Yes, I've got the mark scheme there. So as you do this, the last part of the question, the kinematics, you're using this f equals ut plus a half at squared. You obtain a quadratic, which is certainly not a horrendous quadratic to solve by hand, but why bother? It seems a bit silly to require them to write out the quadratic formula and substitute the values in on the calculator and so on. It's effectively the same thing to simply use their calculator. And note that the mark scheme has on the far right hand side, including BC by calculator. You'll find that throughout the OCR and MEI mark schemes as an indication that there's a step here which you might want to use calculator for. Now, technology in the classroom. So that's sort of thinking about assessment. Of course, that use of calculator, needs to be there in the classroom as well. But from Spec A, we have this statement that the primary use of technology at this level is to offload computation and visualization to enable learners to investigate and generalize from patterns. So this is about using technology to spend time thinking about the mechanics, not plowing through the algebra or the trigonometry or the calculus or whatever else. So rather than doing one example where it takes you 10 minutes to do the analysis, you can do one example, it takes you 5 seconds, and you do another example, and you can start to generalize and gain intuition, gain a feel for intuition. So I've got a couple of demonstrations. One of the great tools for technology is GeoGebra. Now, setting up mechanics situations in GeoGebra can be quite testing. But fortunately, somebody has already done an awful lot of work in setting these up, and let's just have a look at a couple. So if I share a desktop, so this is a resource by a guy called Steve Chung, whose name is up in the top left-hand corner of the screen. If you're at the OCR conferences, one-day conferences, you'll have seen these already. But he's produced a whole series on, and you can look on GeoGebra. He's produced a whole series of these sorts of examples, which are incredibly useful. So this is a classic box on the slope situation. We've got friction involved, so it's a rough contact. So no, that's a rough contact between the two. It doesn't mean that both objects are rough. We talk about rough slopes, meaning it's a rough contact between the two bodies. And simply speaking, here we can click run, and what happens? So the box goes up the slope, and then it starts coming back down again. Simple enough to just try that a few times and start getting a feel for what's going on. Notice it goes up the slope, seems to disappear up the slope a lot faster than it comes back. So the first thing, of course, is that this object is going up the slope to start with. So we have the velocity v0 is minus 7.8 up at the top, and so it's going up, and that means that the friction is acting against the direction of the motion. If you just watch the friction arrow, which is this arrow here, as we go up, you can see it flipping at the top to start coming down. So the resultant force changes at that moment. We can also, another way of spotting it is that the acceleration is given here. We've got a running commentary on the acceleration and velocity. If you watch that acceleration, 9.41 meters per second squared, and at the top it flips. So we suddenly have it very small. So this is why we get this slightly counterintuitive thing of it zooming up the slope and then creeping downwards. All of that coming out of running this simulation a few times to gain the intuition about what it's doing. It was very difficult to do on pen and paper. What's also very difficult to do with pen and paper is to change what's going on. So of course I can now change it so it zooms straight off down the slope. That's easy enough to do. And we can also change the angle of the slope to see what happens with that. And pleasingly on this, we can change gravity as well. If we take it off the Earth, we can do our example on the Moon down at 1.6, wherever that is. I can't quite get it there. Oh, let's do it at 1.8, and we get this. We can see that these forces are now very small. The forces involved are very small. We can also see that it takes quite a long time to decelerate and come to a stop. And we can also see that friction is now big enough to stop the box. That's an interesting idea. We vary the gravity. Suddenly, that little bit of friction is enough to stop the box dead in its tracks when it gets up to the top. Just reset that and see again. So you can see that as it gets up to the top, it just stops dead. Okay, and it's possible then, of course, to get in there and have a look at this force in there and see what's going on. So that's one really nice example. And the sliders, this idea of sliders, allowing you to build up that intuition and generalize about how objects operate and how things work. Another good example is this pulleys example, where again, if I simply run it, we get this sort of situation. And there's something which to many students when they start thinking about pulleys is a little counterintuitive, which is that the mass of the blue object is greater than the mass of the red object, but it's the red one that's as it were winning because of the angles that things are operating at. And it's easy enough to zoom the slider down here to make it a bit smaller. And now it's the blue object that wins. And it's very easy now to set up a little game with students. Can you find the mass at which it stays the same? Those of you who know your mechanics well and know your exact trig values, now on foundation tier GCSE, so they should be there. At a half, we know that if we set it up at 10 and 5, actually that's not going to do anything at all. And we can show numerical values of things going on, which of course isn't very interesting here. If I change the mass, we get the acceleration, we get the tension, we get the velocity. So again, lots of scope here for gaining that intuitive sense of what's going to happen within a context and within an idea, and also of exploration. So you can see how even without knowing how to resolve forces or so on, that it's possible to find the masses at which the thing balances. So it's possible to find that point of equilibrium, and then perhaps to go on and try to explain it through thinking about the way forces operate. So the technology allows, yes, for repetition and for variation, but it also allows for this exploratory aspect, which is again very difficult to do on pen and paper. Okay. The last thing to talk about, and I'm running out of time, so I won't spend a lot of time. Last thing to talk about is practical work, and the possibility of drawing in some practical, some physical work. So everything that I've just said for this simulation work with technology goes double for actually doing things physically. If you have the equipment, the time, the expertise to set up pulleys, borrow stuff, beg, borrow, and steal from the physics department, actually doing this yourself and feeling how the weights change is even better. I appreciate that many of you won't have the time, the space, the expertise, the equipment and so on and so forth to do that kind of experiment, but that's not the only sort of practical work that's out there. We'll just draw on the idea of teaching and learning tasks. It's something that I've been asked already when talking to teachers, which is in the specification. We have using technology, and we have a list of possible teaching and learning tasks, and we have the large data set. We have a list of possible teaching and learning tasks. And the obvious question is, where is the one for mechanics? Now, we did have a list of teaching and learning tasks for mechanics. We chose not to include it in the specification because the first two, the technology permeating the specification and the use of large data set in the assessment, are criteria requirements. So whilst you don't have to follow our teaching and learning examples when you're teaching the course, they are there as examples of a thing that you have to do. Practical work for mechanics is more of a nice to have. It's certainly not a criteria requirement. So we felt that putting in a list of teaching and learning activities might give it the same status and might lead people to think that it was a necessary thing they had to do. So everything that follows now is a nice to have, sort of things that it would be great to do if you can. So why do them? Well, great opportunity for experimentation and exploration, and physical hands-on, actually doing things with your hands and having the opportunity to change and play around with setups and so on. And that direct experience develops intuition in a way which simulations really can't. So if you can get yourself out on the playing field with some balls and get people throwing balls back and forwards, if you get far enough away, you can see that it's almost a parabola but not quite. All those sorts of things. It's simple, direct experience of seeing some objects moving in the way that you're talking about. It's also quite a lot of fun. I mean, getting out on the playing field with some balls and throwing them around is something outside the experience of a lot of students within mathematics classrooms. So getting out and about and doing some physical things and some physical activity within the class is a really good way of having a bit of fun and learning some maths while you're doing it. So where are we going to get, and what do we mean by practicals? I've already said this sort of thing. You don't need lots of access to lots of equipment. If you can beg, borrow, steal things off the physics department, then that's wonderful. But there are lots of things that you could do in group work and discussions. There's a lovely one in the NCPN resource where you have two students, one with a velocity time graph and one with a distance time graph. You get one of them to start sketching something on their graph, and the other has to match on their graph to make it join up. That's effectively practical work. It's a hands-on activity. It's experimental. It's open-ended, and that's the kind of thing we're talking about. It's about playing with concepts and ideas. And where can you find some? Here are two classic sources. We're working on some OCR resources as well with some ideas for practicals. Here are some really good free online examples of practical activities, group activities, and so on that you can build into mechanics activities. And do please talk to your physics department. They're not as scary as you think, and they will have lots of examples of great kinematics, dynamics sort of experiments, and possibly will give you some guidance and some help as to how to do it. You might even manage to operate some room swaps. If your timetabling works, get yourself into the physics labs and use equipment there. I suppose if you could do this 2 or 3 times in year 12 and in year 13, that would be a great thing. Just adds a little something. It's a nice to have, but it would add an awful lot to a student's understanding. Okay. So support and resources I need to talk about briefly. We have the teaching order framework is available on the website. It is set up as a two-teacher model with separate pure mechanics, separate pure and stats. It also has the further maths in there, all 4 options, again set up as a two-teacher model. If once you've decided the 2 that you're going to teach in the sort of main pathway, of course students can take 3 or 4 options with their OCR specifications, but the main 2 you can delete the other 2 and you get a nice structure. So this goes through all 5 terms of the 5-term A level, getting the AS content in the first 2 terms and making sure that all the prerequisite knowledge is dealt with, and the full co-teachability of the further maths options is then sort of exemplified in here. We have the scheme work builder for if you want to do it yourself, of course. All the statements from the specification there in a drag and droppable form, and teaching activities which are on their way, they're coming. Mapping document for further maths looks like this. There's for the options showing which of the current units things come from. Check-in tests, no mechanics ones on the website yet, but they are coming through for us for quality assurance. These are topic-based formative assessment tasks. They start with 3 or 4 routine procedural sort of questions, and then the rest of it is about the overarching themes. Different balances of overarching themes depending on the particular content. Zooming through, we have the CUP. This is all stuff that you've seen before if you've been at any of the other webinars. This is the last webinar, so the last event of the Festival of A-Level Maths week is tomorrow in the Emirates Stadium in London. It'd be lovely to see some of you there. If you've been at one of my webinars, do come up and have a chat. It'd be lovely to hear from you how you think they've gone and what we could improve. We've got these CPD events, 7 CPD events running through the back end of June and July. These are hands-on teaching and learning events for you with some large data set activities, a bit of practical mechanics as we've been talking about today. We'll do some experiments, and also in the afternoons thinking about further maths and so on. If you're planning to teach OCR, please do let us know through the link. It's really useful to us to have an idea of is teaching the OCR or MER specifications, help us to plan and our delivery for the coming term. So that's the end. I'm afraid I've gone on slightly longer than I wanted. We've only got 1 question there, but if you do have some questions, please get typing, and I'll run through some answers. I hope you found that useful. And so let's have a look. We have 1 question here, which is not mechanics specific. Okay. In Monday's webinar on further maths, I talked about the resources, lesson elements, etc. being available on the Maths Hub page of OCR. Couldn't find this. Okay, so we can screen share here. I've got a Chrome page. Yep. So let's do a quick share desktop, and I can show you where these things are. So here is the OCR maths page. You can see the link at the top there, qualifications by subject mathematics. If you're going through from the home page, you can click through on qualifications by subject maths, and you find yourself here at the hub. Blogs here, these are all my current blogs. Newest one is calculators there, just pick that out while we're there. So if you click on the A level, and 230 and 240 maths A, that's the OCR spec, maths B the MEI, and here further maths A and B. And if we click on here, there's sometimes a bit of a pause on this load, which it appears to be today, I'm afraid. There we go. So this is then specifically the Maths A specification page. If you scroll down, we have specifications, assessment materials, and then in teaching and learning resources, we have check-in tests here, 1 on algebra and functions, 1 on conditional probability, and a guide. So these will be for every topic in A-level maths. They're coming through us, as I said, for quality assurance. Got some lesson elements with large data set elements in there, and some teacher guides. This is where you can find the superb bridging the gap guide for GCSE and A-level, which a developer has written based on something that his school does, and the various mapping guides and the teaching order framework that I mentioned. So that's where to find things. That's now, of course, recorded, so you can always come back to this recording to find them. Okay. So if there are any more questions, do please fire them off. Yes, it does look incomplete. I'm afraid that's what's there at the moment. and the focus on accreditation and the short timescales between accreditation and first teaching make life a bit difficult. But there's a huge number of these resources that's coming through OCR at the moment, which we're trying to get quality assured and tidied up and out on the web as soon as we can. So you should see those starting to build as we go through the back end of the summer term and into first teaching. And in the first instance, focused on the sorts of things that appear in our scheme of work in that first term. Okay. So no more questions coming along. We've now hit 6 o'clock. So if that's it, thank you very much for coming. And I hope you've enjoyed these webinars. And I hope to see some of you tomorrow at the A-Level Maths Festival. Do come and bother me and ask any questions then. Thank you very much.
Thanks very much, Will, and thanks to you all for joining us for this online event. We hope you found the session useful. A full recording will be emailed out to everybody. If you have any feedback, please do complete the short survey that will appear when you have logged out. Thank you.